Okay, so we finished up chapter 1 yesterday. Today we're going to jump headfirst into chapter 2. Chapter 2 is all about solving equations, especially these first two sections. Today we're actually going to learn about two of the most common tools that we use to solve equations in algebra: the multiplication principle and the addition principle. Those two tools, if used properly, will help you to solve pretty much any equation you might run into in this class. Okay, so let's talk about, before we begin, let's remind ourselves, what is the difference between an equation and an expression? Yeah, expressions sort of say something. Equations say something about something, right? And so an expression would be the Seattle Seahawks football team. An equation, right? Would be whatever your opinion of that team is.
The Seattle Seahawks insult here.
Yeah, right? There's a big difference between 2x and 2x equals 1. So let's just keep that in mind as we go along through this chapter. Because in this chapter, we're talking about equations, not expressions. And the equations, this little equals sign, gives us an invaluable tool that we can use. All right, so let's talk about equations and their solutions. So equations, as we've said before, is basically just a number sentence that, that states that the expressions on either side are the same, right? And so this first line here, the equation 4 plus 2 equals 6, that's a true equation. So we're allowed to use the equals sign. That is true. But this second line, 3 plus 5 equals 2, this is false. So we should not use the equals sign, right? This is what it means to be non-equal, right? That's notation for something that's not equal. So if you say, well, I know that the variable is not equal to 2, you can say, well, x certainly does not equal 2. We know that much. All right, so then the third line here, this equation 1 minus 2 equals negative 1. That's another true equation, right? But what happens when we throw a variable in there? What if we consider this equation? X plus 1 equals 2. Well, that equation only becomes true if you replace x with the right value. Otherwise, it's false. The right value happens to be 1 for this case. Right? So x equals 1 would make that a true equation. So the official solution to an equation is any replacement for a variable that makes an equation true. Right? And so on that last little example, x equals 1 was a solution to this equation because when we plug it in, it made it true. Okay, so that's called a solution. If you're asked to solve an equation, that means you find all possible solutions that make it true. All right, so if somebody gives you a solution and you want to know if it is a solution to a given equation, we set up a table. So if we want to test this equation for this particular solution, we write out the table, and the vertical line in the middle sort of it gets placed wherever the equals sign is. Oh yeah, please, go ahead. No, it's fine. I'll just... So we have a student disrupting the class, sharpening their pencil right now. I'm just kidding. No, that's totally fine. Okay, so what we want is x plus 6 on one side, right? The equals sign goes in the middle, and then we have 13 over there. Okay, so what we do is, as we go down line by line, we replace x with the proposed solution, and we find out if this is true or not. So instead of x plus 6, I write 7 plus 6, right? That still should equal 13. On the next line, I go ahead and do my addition, and I find out that 7 plus 6 is 13, right? If I reach a line in this test where everything is true, I say, yeah, that is a solution. So, yes, that is a solution. Okay, if I reached the last line and it gave me something that was not true, then that's clearly not a solution. All right, so in this next one, they asked me to determine whether negative 1 is a solution to this ugly thing. All right, so I just set it up with my table. I place the equal sign in the middle, so I have 7x minus 2 on my left side. I have an equals sign in the middle, and I have 4x plus 5 on the right side. Now I replace my x with a negative 1. Okay, so 7x becomes 7 times negative 1 minus 2. 4x becomes 4 times negative 1. And then I have a plus 5 over here. Okay, on the next line, negative 1 times 7 is negative 7 minus 2. Negative 1 times 4 is negative 4 plus 5. And so here I have a negative 9 on my left side. On my right side, I have a plus 1. That's not a true statement. So this is not a solution to this equation, right? Boom. Nope. No. So that's it, right? If you want to tell if a solution is valid, this is how you check it. We only focus on this for maybe this one section, but this can come in really handy throughout all the exams. It's very rare that students in this class actually check their work on exams, but when they do, their grades go through the roof. Because you can check your work and say, oh, I got that wrong. I must have messed up on a small step. It's very rare that students do that in this class, though, so don't forget this. This is really important to be able to know how to check your work easily. On some problems, I can't blame you. They're too ugly, and I just want to say, well, I'm just going to assume I'm correct. But on other problems, it might take you like 3 minutes to check your work, and that's worth a full letter grade possibly on an exam. All right. So, moving on. The first main tool that we're going to talk about today is called the addition principle. So, to illustrate the addition principle, first of all, let's think about a very basic equation. The basic equation, x equals 3. We can make that a true statement by replacing x with 3, obviously, right? So the solution to this equation, the first equation up here, is 3. Equation B, that's just a true statement. Okay, so now let's consider this next one. We have x plus 2 equals 5. Well, in order to make this a true statement, we would again replace x with 3, just like we did in the last one. All right, so if we solve this equation, we boil it down to exactly what the other equation was. That means that these two equations are called equivalent. Okay, it seems weird that this equation is somehow equivalent to this one down here, because they don't really look the same. But any equation with the solution x equals 3 is considered equivalent. All right, and so it could be any mess of craziness on there. As long as the solution is just x equals 3, it's equivalent to this original basic equation. Okay. All right, so let's go over some examples of equations that are equivalent to x equals negative 1. This first one, A, right? If x were equal to negative 1, I would have negative 1 minus another 1. That gives us negative 2, so that's an equivalent equation. All right? 2 times x equals negative 2. Once again, that's equivalent, because if you plug in negative 1 for x, it makes this a true statement. Okay, on this third one, let's test to see if it's a solution or not. So we have 3x plus 9 equals negative x plus 7, and I can draw out my table just to make sure that these actually are equivalent. So I replace my x with a negative 1, so 3x becomes 3 times negative 1 plus 9. And then on my other side, I have a negative x, which ends up giving me a double negative. All right, and so I do one little bit of arithmetic for each line. 3 times negative 1 gives me negative 3 plus 9. That is equal to a double negative on the 1 gives me a positive 1, so I have 1 plus 7. 9 minus 3 equals 6. And, oh, did I do that wrong? Nope, it's just not an equivalent equation. Huh, that's funny. So I guess maybe I planned that out last year and forgot about it, but this equation does not actually work out because I have 6 equals 8 down here, so that one's not, that one doesn't work. Okay, so now we're gonna go through just a few more of these to recognize this pattern that should start jumping out right about now, especially when we go through these ones. So let's start with the basic equation y equals 5 up top. Okay, so we can create an equivalent equation to that by adding 3 to both sides. See, if I add 3 to y on the left side, and then I add 3 to the 5 on the right side, I've created a true equivalent equation. Same thing happens if I add 2 to both sides. Right? I've increased the 5 by 2. Same thing happens if I add 1 to both sides, right? So I can keep creating equivalent equations by adding or subtracting things for both sides. You can see in this example, E, I've added 0 to both sides and got the original. As I go downwards, I've started subtracting things from both sides. So this is y minus 1, right? I've subtracted 1 from that side as well. So that's the pattern of equivalent equations. You can see we're allowed to add or subtract things from both sides, as long as we do it to both sides, and we maintain the equality. That's important. That leaves us, oops, there's our definition of equivalent equations again. Right? Equivalent equations are those with the same solutions. Oops. There we go. That's what I was getting to. So out of all the ones above, y equals 5, that's in the best form because we know what the solution is. It's just the equation. Okay? But all that whole pattern leads us to the next rule. The next rule is the official addition principle. All right, so this principle says, if you start out with A equaling B, then you can add any constant term C to both sides and still be good. Okay, so that's really important for what we're about to do. Okay, so now let's think about this. Why does this not work with expressions? Right? Why would this addition principle work over here on this side, but not on this side? Because there's no equal sign, right? There's nothing to say like this is equal to something. The equal sign having a balance, it's like a balance beam, you know, like a beam scale or something like that. If I have an equal weight and my arms are at the same elevation, I can't add 5 pounds to one side and 2 pounds to the other and have it work out. It's got to be the same thing on both sides. And so that's what this is getting after. An expression doesn't have an equals sign, so there's nothing to add to both sides, right? And so this is a tool that we use with equations only. Okay, so let's do some examples on how this is used to solve equations. So what we do when we solve equations using the addition principle is we want to isolate the x, right? In this example A, by this last line, I want it to say x equals some number. So what I'm going to do is I'm going to add something to both sides that's going to allow me to isolate that x. Since the x is attached to a 5, what I do is I add the opposite of 5 to both sides. And so I say I'm going to say x plus 5, and then I'm going to subtract 5 from that side. Then I'm going to say that's equal to negative 7, and I have to subtract 5 from that side as well so that I can keep them even, right? Now we can cancel something. Plus 5 minus 5, that equals 0. So I just cancel that out on this side. And on the next line, I have my x isolated. Negative 7 minus 5 more, that gives me a negative 12. And so that's it. So that's how we use the addition principle, right? We look at our x and we say that's attached to a number I don't want there. So I am going to add the opposite of that number to both sides. Okay, let's do the same thing on example B. So I notice that x is attached to a negative 2, right? I want x to be alone. So what can I add to both sides to get rid of that negative 2? Yeah, a positive 2. All right, so that leaves me with x minus 2 plus 2 equals a negative 4 and then plus 2 again. All right, we got to make sure that we add that 2 to both sides, otherwise this does not work. Okay, so the 2's will cancel each other out, and then we get x is equal to negative 4 plus 2, which results in a negative 2 total. Okay, on this next one, it's roughly the same thing, right? The decimals don't change anything, right? We say, okay, I want to solve for this variable right here, for y. Y is attached to a constant term. That term is negative 8.4. So I need to add the opposite of 8.4 to each side. All right, so 8.4 is a negative, so I need to add things this time. Plus 8.4. And I'm going to say 8.4 over here, right? These guys will cancel. And I'm going to get 8.4 minus 6.5, which is 1.9. And that is equal to y. Okay, even if it's a big number, doesn't matter, right? We just add the opposite to both sides so we can isolate that x. All right, x is attached to 3,145, so we add that to both sides. So I say x minus 3,145 equals 22,000, and then I add the opposite of 3,145 to each side. So I say plus 3,145 plus 3,145. Just like I wanted, these guys will cancel out, and I end up with x equals 22,000 plus this stuff, which is 3,145. What's that?
Too many at that comma, sir.
Oh. Thank you for that. Wow, that was way off, wasn't it? Sorry. 25,145. That's a great way to state that. You have too many numbers after that comma, sir. Excellent. Okay, so there it is. And hopefully, when I would have checked my answer on that one, I would have caught that boneheaded mistake. Hopefully. Okay, so that was the addition principle. Okay, these first three scenarios, these are, like we use the addition principle. Notice how the x is attached to something through addition or subtraction, right? That's when we use the addition principle to get rid of that thing that it's attached to. Right? So we would add it to both sides or add its opposite to both sides, and then we would have a solution. Right? And so, that's kind of the situation when we use the addition principle, when something's attached to x with plus or minus. However, a lot of the time, it's not attached to x with plus or minus, it's attached with a multiplication. Right? And so when we have equations that say something like 3 times x equals 15, we also need to know how to isolate x on that. Right? That doesn't do me as much good as x equals some number, right? This is always your end goal when you have an equation they ask you to solve. You want x equals some number, right? 3x equals 15, close, but I don't accept that. I gotta have just plain old x. Okay, so we use the multiplication principle to manipulate this, so it's just a single x equals a number, okay? So the multiplication principle says, it's a lot like the addition principle. It says that if you have a given equation, a equals b, you can multiply that equation by the same thing on both sides and not change the value, okay? So once again, we have an equal sign. We just need to make sure that we do things on both sides of that equal sign. Okay, so let's go ahead and try out solving this guy. All right, let's try to solve 3x equals 15. So first of all, let's ask ourselves, what are we trying to isolate in this? Well, yeah, there's only one variable, right? That's kind of an easy question. We're trying to isolate the variable x. What number do we have to turn into a 1? The 3, yeah, the coefficient on the variable, right? So 3 is the number that we need to turn into 1. What's the reciprocal of 3? 1/3, right? Whatever. Noelle, you're so energetic today. So the reciprocal of 3 is 1 over 3, right? If we multiply 3 by 1 over 3, we turn it into 1. So now that we know what the reciprocal of that is, we know that we need to multiply both sides of this equation by the reciprocal, 1/3. Okay, so I say, okay, 1 over 3, 1 over 3. All right, on the next step, I'll end up with 3 over 3x equals 15 over 3. 3 over 3 just equals 1, just like we wanted it to. Right, and so now we have x equals 15 over 3, and we know that that equals 5. Okay, so that's it. When you need to use this, you just need to make sure that you're in the right situation to use it, and we're going to talk about what situations to use this in and not to use this in a little bit. But when you're in some situation like this, when you have some number times a variable equals another number, this is a perfect way to solve it every time. Speaking of that situation, here we are again. So in this one, we are trying to solve for x. The number attached to x is 5/4. Right? What is the reciprocal of 5/4? 4/5. All right, so I multiply both sides by 4/5. All right, this side cancels, gives me 1. So I end up with x is equal to 10 times 4 over 5. That is 40 over 5. And 40 over 5 is just equal to 8. If you're wondering how I got 40 over 5 there, it's because I multiplied these two fractions together, and this fraction is just 10 over 1. Okay? All right. What's that?
Well, when I do it, I just multiply both sides by 4, and I'm just giving myself x instead.
Yeah, and there's multiple different ways to look at this. Multiplying by the reciprocal is one way. Some people say divide by the coefficient. At first, concentrate on multiplying by the reciprocal, and then fall into whatever routine you feel comfortable with. Personally, like I always say, oh, just divide by whatever is multiplied by x, and you'll see what that means in a little bit here. But for now, definitely focus in on the reciprocal part. Okay, so now if we're asked to solve this one, we say, okay, what are we solving for? X. What's the number attached to x by multiplication? Well, that's a -4. What is the reciprocal of -4? Yeah, 1 over -4, or -1/4. Okay, so if I multiply both sides of this by a -1/4, okay, everything ends up canceling in front of the x because I just have -4 over -4. And so then I have x equals a 9 over 4, and that is negative. Okay? All right, sometimes you'll reach the end of an equation and it doesn't look like there's a number in front of x, but there actually is. Okay? When there's a negative sign in front of x, that means there's really a -1 in front of x, right? And so it's kind of basic, but we do the same thing. We say, okay, we want to solve for x. The number in front of x is -1. What's the reciprocal of -1? Yeah, 1 over -1. Yeah. Or in other words, -1, right? -1 is its own reciprocal. So we multiply both sides by -1. And we end up with a positive x now equals 5 times -1, which is -5. Okay, so if you have an x in front of if you have a negative in front of your x and you don't want it there, you can just swap all the signs of everything in the whole equation. Okay. So using the correct approach. So these are two examples. Right? These are kind of the most basic things that you'll run into. A lot of times you have to use both of these tools together on the same equation, but this top example is a great example of when you would use the addition principle, right? Because this -8 is attached to the variable through addition or subtraction. To solve this, we would add 8 to both sides. So I would say, okay, plus 8 over there, plus 8 over here. These two 8s would cancel, and I'd have x equals -3 plus 8, which gives me 5. Okay, this is a perfect example of when to use the multiplication principle, because I have this little coefficient out in front of my variable. Nothing's added or subtracted to it. It's just attached through multiplication. So we use multiplication to break that attachment. Right? And so what I would do is I would multiply both sides by 1 over 0.3. 1 over 0.3. Right? Which means these 0.3s would cancel over here. I'd end up with 18 over 0.3 equals t. And then, of course, I'd break out my favorite tool, the calculator. And t equals 60. Right? And so those are kind of the visual cues to let you know when to use one tool or the other. But we're going to go into that in a little bit more detail in the next section. This next section, we start putting all this stuff together to where we have to use the addition principle first and then go to the multiplication principle. So these are the typical steps to solving an equation, right? The first step is we apply the addition principle as many times as it takes to isolate the variable, right? What I mean by isolating the variable is getting an equation that looks something like this. AX equals B, where A and B are just numbers. They're just constant terms, right? It could be 2x equals 3. It could be 10x equals 5. It could be -500x equals -3. You know, it's just any numbers, anything that looks like this, it's time to use the multiplication principle. Until you get to that spot, you keep using the addition principle. Okay. So once you get to that spot, AX equals B, that's when you use the multiplication principle and you multiply both sides by the reciprocal of A. So let's go to the first example here. So what I want to keep using the addition principle until I have something that looks like this, AX equals B. All right, so I notice my x's are over here. They're attached to 5 through addition. So I'm going to get rid of that 5. I'm going to add the opposite of that to both sides. So I can say, well, I want to subtract 5 over here, and I want to subtract 5 over here. These two 5s will cancel out and give me 0, and I'll have 3x equals 17 minus 5, which gives me 12. Now I'm in this situation, AX equals B. Right, where my A would equal 3 and my B would equal 12. So now I'm in that situation, so I can use the multiplication principle. I notice that 3 is the coefficient, so I want to multiply both sides by the reciprocal of that coefficient. So this is multiplied by 1/3, and so is this side, multiplied by 1/3. Okay, the 3's will cancel each other out, and I'm going to end up with x is equal to 12 times 1 over 3. 12 over 3. If you punch that in your calculator, you'll find out that that is just equal to 4. Okay, so we use the addition principle until we reach the step that looked like AX equals B. Then we use multiplication. All right, let's keep going. So on this one, here's my variable. I can't do a multiplication principle yet because it's attached to something using subtraction. So I want to get rid of this thing it's attached to a subtraction. So I add the opposite of that to both sides. Okay, so I end up with 4 over 3. Oops, that's 4 over 4. Don't want that. 4 over 3 x minus 7 equals 1. And then I'm going to add 7 to both sides. Plus 7 plus 7. Okay, these ones will cancel out because that equals 0, and I end up with 4/3 x equals 1 plus 7, which is 8. Okay, so now here I am. AX equals B. Now I use multiplication. What should I multiply both sides by? Yeah, wait. 4/3 or 3/4, right?
Oh no, okay. So
3/4,
okay,
right?
okay.
Yeah.
Sorry, I was working ahead and I did it.
It's all good. Remember, that's part of the class, right? If you're not getting stuff wrong in math, you're either shouldn't be in this class or you're not speaking up enough. All right, so these guys cancel out. Give me 1. That means I get x equals 8 times 3/4. This is secretly an 8/1. All right, so I have 8 times 3. That gives me 24 over 4. What? Am I wrong?
I'm not good at my 3 times 3.
All right, so I'm not good at my 7 times tables. 7, I don't remember any of the 7s except for 7 squared. That's it. And 7 times 2, I got that one too. All right, so for this one, same thing, right? And actually, we got a little bit of time. Why don't you guys work this one on your own? I'll give you a few minutes to do that, and then we'll come back and work it on the board. I know, it's terrible. I'm a tyrant.
Yeah, do it on the back of my quiz.
I liked the cookies the other day, by the way. They were excellent. Oh, it's permanent record. I edited it, so I edited it out of the YouTube video. It's just not there. It'd be terrible. Okay, so for this problem, first thing we notice that we want to solve for this negative t in here. It is attached to the 45 through addition, so we want to add the opposite of 45 to both sides. And when I say add the opposite, that doesn't always mean we're adding a positive number. Sometimes we're adding a negative number, as you've seen. So I say plus a negative 45 on both sides. These two 45s will cancel out, and I end up with negative t equals 13 minus 45, which is, thank you, negative 32. Okay, and look at this. Both of these have negative signs, so if I multiply through by a negative 1, those just go away. T equals 32.
That's what it's like. I know there's.
Right? Yeah, sometimes that's a little bit weird. Yeah, it's just you multiply through by a negative 1, and if you're like, well, I really want to show my work on that step, which is good. I should have showed my work. you can say, okay, -1 on both sides. I guess you'd have to do that too. All right. Moving on. Sometimes we have decimals. It's the same operation, right? We want to isolate the y, so we have to get rid of these things that it's attached to by addition. So that means we have a positive 16.3 that we need to subtract from both sides. Okay, so minus 16.3 minus 16.3. Oops, put a little plus sign in here. These two will cancel out, and I have negative 7.2y equals this stuff. Nice job. There you are. So that is a negative 24.48. All right. Now I am going to multiply both sides by the reciprocal of y. Sorry, the reciprocal of the coefficient of y. The coefficient is negative 7.2, so I'm going to multiply both sides by a negative 1 over 7.2. Okay, so on the left side, things cancel out, just like we wanted them to. On the right side, we're going to have to punch that guy into our calculator because it's kind of ugly. We notice that there are two negative signs, so those are going to cancel each other out. So we'll have 24.48 divided by 7.2. And that leaves us with 3.4. Oops. Okay. So basically, that's it. You kind of just keep doing that and using the multiplication principle until you get to one of these situations, right? These are all the situations that are really nice. All of these are examples of ax equals b, right? For this first one, we would multiply both sides by 1/4, right? For this next one, we'd multiply both sides by what? 1 over 11. On this next one, negative 1 over 2, right? That's how we would solve that one because the coefficient is negative 2. This one here, we would multiply both sides by the number 5. Okay? And then this big ugly guy here, let's just do that one. We would multiply both sides by 1 over 0.836, right? And so, and I guess this is a good time to show you this different notation. Multiplying something by 1 over a number is the exact same thing as dividing by that number, right? And so instead of saying I'm going to multiply both sides by 1 over 0.836, I can actually just divide both sides by that number. It's equivalent. Okay, if you prefer the 1 over, stick with that. You know, don't let this confuse you, but you know, it's equivalent. I'm sort of skipping one step. Okay, so these guys would cancel, and I'd end up with x equals 0.635 divided by 0.836, which would give me something really super ugly. I'm just going to estimate it, so I'm going to use my little estimation equals sign with the curved lines. This is roughly equal to 0.76, we're going to say. Yeah. Okay. So, sometimes we run into different things. Sometimes they have not combined all the like terms before we begin these equations, right? Like this one. These are not combined. We haven't really seen that yet. If they're not combined yet, combine them. That's all. So with this one, right, we just say 3x and 4x, those are like terms. That's going to boil down to 7 x equals negative 14. And then we would multiply both sides by the reciprocal of 7, which is 1 over 7. The 7's will cancel, and we get x equals negative 14 over 7, which is negative 2. Okay, so that's one way that that's one thing that we're going to see when things aren't fully combined when we start. We want to combine them if we can, but sometimes we run into, I don't know, I was feeling dramatic when I wrote this, I guess. Sometimes we run into variables on both sides of the equation. You got a question?
We don't combine like terms first, though, if they're separated by parentheses.
If they're what?
If there's a parentheses.
Yes, no, yeah, don't break the rules of parentheses trying to combine like terms. That's a good point, yeah. Make sure you free everything up first before you combine them, yeah. Yeah, you got to keep with the proper rules of operations. Okay, so when we end up with variables on both sides of the equations, I typically just choose one side that I'm going to collect all my variables on, and I go about doing that. And so for this particular equation, I'm going to put my variables on the left and my constants on the right. Okay, and so what I mean by moving the variables over is we use the addition principle to move things back and forth in an equation. So if I want to take this 8x and I want to toss it over to the other side, I can use the addition principle to do that. So I do that by adding its opposite to both sides. So I'm going to say plus 8x over here, and I'm going to add 8x on this side as well. So the 8x's on the right side go away because positive 8x minus 8x equals 0. Okay, so the ones on the left side are still there. So I have 8x minus x. That leaves me with 7x. My 5 is still there, and my 6 is still on the other side. Now I'm in a familiar situation where I can just add the add the opposite of the constant term to both sides. So I have 7x plus 5 equals 6. What I want to do is subtract that 5 from both sides, further isolating my x. These guys go away, and I end up with 7x equals 6 minus 5, which is 1. All right, now I'm in the final step. I have ax equals b, so I multiply both sides by the reciprocal of this coefficient 7, which is 1 over 7. All right, so these guys cancel, and I end up with x equals 1/7. Any questions on these? Pretty basic, yeah. So it just helps. I noticed it helps to choose a side to put your variables and your constants on. Not everybody has a problem with it, but some people tend to get writer's block when they see this, and they say, "Well, I don't know what to do. I'm just going to start adding variables." And they'll add a variable to one side, and then they'll subtract a variable to the other side, and you'll have to say, "Well, did you complete anything? Like, did we move forward?" And so it helps when you choose a side to move all your variables to and just do that, right? It helps with writer's block a lot. Okay, so here we are with this one. Okay, we notice we have variables on both sides. Just like we always do, though, we're going to try and combine any like terms we can before we start this. Okay, we notice on the left side, I have like terms with the 6x and the negative 7x. 6 minus 7 gives me negative 1, so that's negative x, plus 5 is still there. Over on the right side, I have negative 4x, and then I add my constant terms together to give me a plus 17. Okay, so once again, I'm going to throw all my variables over to the left side and all my constant terms over to the right side. First things first, I'm going to move this 4x, this negative 4x, over to the left side. So to do that, I add its opposite to both sides. Plus 4x and plus 4x. All right, over here on the right side, these guys cancel out because they equal 0. On the left side, I have 4x minus x. That gives me a 3x, plus 5 is still there, and on the other side I still have a straight 17. Okay, here we are in familiar territory again. So we want to isolate that x. We're going to add the opposite of 5 to both sides. So I say minus 5, and I end up with 3x equals 17 minus 5, which is 12. Okay, here I am in ax equals b territory once again, so I'm going to multiply by that reciprocal, 1 over 3, and I end up canceling those 3's, and I get x equals 12 over 3, which is equal to 4. All right, let's keep on going here. So let's see. Okay, so this is kind of the other variation. This is what Noel was talking about earlier. Sometimes you can't just jump right in and start combining like terms. Sometimes you want to get rid of those parentheses first, because right now we're sort of stuck. We can't really combine like terms. So to get rid of the parentheses, we do what we always do to get rid of parentheses. We start distributing. All right, so the 2 stays there, and I distribute this negative 5 into each term. So I have negative 5 times x. That gives me negative 5x. Negative 5 times 5, that gives me negative 25. Over on the right side, I distribute this 3 in to get 3x. I distribute the 3 in one more time to get negative 6. And I have the negative 1 that just hangs out. Okay, so now I go about my usual process of combining like terms. All right, over here on this left side, I have a negative 5x, I have a 2 and a negative 25. That leaves me with a negative 23. And that is equal to 3x minus 7. Okay, so I'm going to put all my variables onto the left side. In order to do that, I need to add the opposite of the set of variables I want to move over there. So I'm going to subtract 3x from both sides, minus 3x, minus 3x, 3x minus 3x equals 0. Negative 3x minus 5x, that gives us negative 8x minus 23 equals negative 7. All right. One step at a time. So, I want to get rid of this 23. I want to isolate that x. So I'm going to add its opposite to both sides. So I have plus 23 plus 23. These guys cancel out. I have negative 8x equals, oh, let's see now, what is that? 16? Yeah, 16. Okay, so if I have a negative 8 for coefficient, what do I multiply both sides by? Yeah, negative 1 over 8. Negative 1 over 8. Negative 1 over 8. Okay, these guys on the left cancel, and we have x equals a negative 16 over 8, which we know is negative 2. Okay, so that was combining the concepts. Definitely get used to that. Those, yeah, that can be a bit of a drone, sorry about that. But those are used all the time. That's why I try and do a lot of examples. So let's move on to something else that is very, very handy. This is something that students rarely use at this level, but man, if you use it, it helps out a lot. So we typically do not like fractions in equations, or anywhere else for that matter. When we solve equations, it's not too hard to clear all the fractions, right? When we talk about clearing all the fractions, we do that by multiplying every single term by a common denominator. So we'll go over this a couple times, and I just want you to just sort of pay attention to why this is different from when we don't have an equals sign. right? In the last quiz, we did these, we added fractions without equal signs, and we did it in a certain way. But the equal sign is a really great tool. It allows us to multiply through by a single number and not change the value of the equation. So this is how we clear fractions when we have an equal sign. Okay, if you see any equation with fractions, first of all, you find the common denominator. Okay, so we list our denominators on the side, 3 and 6. And this is the same process that we went through to find the common denominator when we add fractions. So we list their prime factorizations. 3 is just equal to 3. 6 is equal to 3 times 2. Okay, we notice that one of these factorizations completely contains the other. So that's the common denominator we're going to multiply through with, right? 3 times 2 equals 6. Okay, so this is how to set this up. So you draw parentheses around both sides of the equation, and you multiply by 6, right? You throw a 6 on the outside. Now we distribute the 6 into both of these terms. So in this first term, I have 2 times 6, which is 12, over 3 times x. Okay, so I just multiplied the 6 into this first fraction. That's all I did there. Now I'm going to multiply the 6 into the second fraction. Right, and so that gives me 6 times 1, yeah, which is 6 over 6. Okay, so that's good. On the right side, I have 6 times 2x. That gives me 12x. Okay, now this is the important part. Now let's go through and simplify any fractions that we can simplify. 12 over 3, what's that equal to? 4, yeah. So I have 4x. 6 over 6, that's just equal to 1. 12x, that's not even a fraction, so we're going to leave it. Okay, so now after I've done that step and I multiplied through, there should be no more fractions. If there's still a fraction on this step, something went wrong somewhere. Okay, after that step, all the fractions should be gone, and we should be able to just solve things in our usual way. So for this particular equation, I'm going to go ahead and solve this. I want to get all of my x's over to one side. This side, or sorry, not this side. For this particular equation, I just noticed that it's going to be easier to throw my x's over to the right side. Right? And so I'm just going to do that instead of the left side on this particular equation. Right? So I say I want to take this 4x and I want to toss it to the other side. So I'm going to add its opposite to both sides of this equation. So I have plus a negative 4x minus 4x. The 4x's go away, and I have negative 1 equals 12 minus 4x, which gives me 8x. Okay, so now I multiply both sides of this equation by 1 over 8. Oops. These guys will cancel, and I'll end up with negative 1 over 8 equals x. All right, moving on. This is a pretty handy one right here. So if we didn't use this little trick, we would have to distribute this 2/5 into each of these terms, figure out fractions, probably clear fractions afterwards. Instead of doing that, we're going to clear fractions on this very first step. So I noticed that my big fraction that I have to deal with is 2/5. Rather than distributing that into both sides, what I can do is I can multiply both sides of this equation by something that clears the fraction. I can just multiply it by its reciprocal, 5/2. These will cancel out because it gives me 1. And then the parentheses go away because there's nothing outside of them holding them in place anymore. So I end up with 3x plus 2 equals 8 times 5 over 2. 8 times 5 is 40 over 2. All right, so now I subtract 2 from both sides so that I can isolate that 3x. So minus 2 minus 2. That gives me 3x equals 20 minus 2, which is 18. Okay.
divided by 2 is 20.
Sorry, I skipped a step there. So the 40 over 2, that's equal to 20. And then I just had negative 2 on that. I should not have skipped that step. That was bad. My apologies. So we have 3x equals 18. Now, multiply both sides by 1/3, just so I can clear that coefficient. And I end up with x equals 18 over 3, which equals 6. Oops, that looks like 16. Okay. So for decimals, since I let you guys use calculators, decimals really aren't that big of a deal in this class. But if you want to clear decimals, this is the way to do it, right? And so you just recognize how many decimal places we have in a given problem, right? And so these two have 1 decimal place. This one over here, this number has 2 decimal places, right? And so I need to multiply through a power of 10 with the same number of zeros as decimal places. That's a complicated way of saying I'm going to multiply this through by 100, right? If the decimal places were 3 out, I'd multiply through by 1,000. If there were 5 decimal places, I'd multiply by 10,000, and so on and so forth. So I multiply each side of this by 100. And 100, when you multiply by a factor of 10, it has the effect of basically just moving the decimal place over. So when I multiply 16.3 by 100, I just move that decimal place over 2 times. So I have 16.3. That decimal needed to move over 2 times, right? And so it moved over from 16.3 to 163 to 1630. Okay. Now, when I distribute the 100 into the second factor over here, I end up with negative 700. And whoops, nope, that's wrong. I end up with negative 720. Okay. And then on the right side, I do the same thing with the factor of 100, and that leaves me with negative 818. Right? And so, whoops, I forgot my y here. So in that way, I've cleared all the fractions by just kind of making these into large numbers. So you can absolutely do that as well. Okay, so to solve this guy, of course, I would subtract 1630 from both sides. These guys would cancel out. Over here on the left, I'd have negative 720y equals 818 minus 630. Oops, 1630. And that gives me a negative 2448. Okay, so I treat this the same even though it's a large number. So I multiply both sides by the reciprocal of 720, of negative 720, excuse me. So I have 1 over negative 720. And this side is also multiplied by 1 over negative 720. These guys will cancel on this side, and I have y equals a negative 2,448 over negative 720. We'll go ahead and punch that guy in. Oh, yeah, sorry about that.
I didn't carry the negative on the 8.
Ah, yeah. Oh, I see. So you just got the difference instead. So when I punch these guys into my calculator, I end up with 3.4. Since there were double negatives going in, they cancel each other out, and the result is a positive 3.4. Okay, so that was today's class. Just remember, we went over the multiplication principle, right, which we use in an AX equals B scenario. Addition principle, that's what we use when we have something attached with multiplication or addition. And we also went over clearing fractions, right, because we hate fractions and we want to destroy them all. So that's that. Thank you again for your patience. There are 3 practice sheets up here, voluntary if you want to practice them. One is fractions. Oh, there, grab a copy of those. And then I have a bunch of copies of order of operations for both algebra and numerals. These have all the answers on the back. So if you want to do these for practice, please feel free. Don't forget we have a quiz on order of operations on Tuesday. Just another one of those simple quizzes. What's up?
What is the symbol for almost equals?
Oh, good. So almost equals, you would say that one, roughly equals. It's those squiggly little lines, yeah.
Okay. Can I show you a question?
Yeah.
This one is guaranteed, right?
Yeah.
Ready?
What you got?
This one.
Oh, here, let me turn this off real quick.